Hello, and welcome. My name is Jake Taylor. I am very pleased to present this keynote here on the last day of the IEEE Quantum Week. Thank you so much for coming, tuning in, and listening, and I look forward to hearing from you at the end of this session when we'll have an interactive period. Before this talk, you probably heard from Undersecretary Paul DeBar from the Department of Energy, who described some incredible efforts to advance quantum information science across the nation, both through the research and also through industrial effort. For my part, I'm here to describe some of the frontiers that this field has ahead of it, and to provide some of the perspective of where we are in implementing research and development enterprises to enable the progress we need to realize those frontiers. I'm currently a fellow at the Belfer Center at the Harvard Kennedy School, and also a fellow at the Joint Center for Quantum Information and Computer Science, the Joint Quantum Institute, and my home institution, the National Institute of Standards and Technology. If you'd like to find me after this talk, not on this platform, I am generally found on Twitter at quantum_Jake, and of course can also be reached out over email. I look forward to hearing from you. Now, with those remarks out of the way, let me tell you about this beautiful picture that you see in front of you, because this represents one of the current frontiers of quantum information science. This, of course, is an optical lattice clock in Jun Ye's laboratory out in Jilla, one of NIST's joint institutes. In these optical lattice clocks, a collection of ultra-cold atoms are held and interrogated with a very narrow laser system. The oscillations of light up at 200 terahertz are the actual clock signal in these clocks. And one of the most amazing elements of this technology is its ability to put new ground down in absolute accuracy, reaching now a part in 10 to the 18. And if you can't imagine what that looks like, just know that that's more accurate than a second drift over what we think the lifetime of the universe is. And these clocks don't come for free, they don't come from nowhere. They're the result of decades of progress in understanding atomic physics, understanding lasers, understanding control electronics, understanding atoms and how they move and how to keep them cold, and understanding what limits such systems in their performance. Today we're going to dig in on this and other topics. The story about quantum information science is really the story of base technologies. I think many of you are familiar with Ramsey interferometry. In a Ramsey interferometer, you have a two-level system, a quantum bit, which is held in a superposition of two different possible states. So here I've labeled these as 0 and 1. And using this sort of Bloch sphere, you can imagine you initialize it so it's initially pointing down. You use a microwave pulse or optical pulse to rotate it to be along the equator. Then it can precess freely around the equator, and that free precession goes at a rate given by the internal physics of that atomic system, or whatever your qubit may be. At the end of that free precession period, you then apply another pulse, which will tip it up towards one of the top or bottom areas, depending upon how aligned it was with the rotation axis that you chose. At the end, you then measure, did it come out as a 0 or did it come out as a 1? And what this allows you to do is to synchronize the pulse source responsible for the Rabi pulses here and here with the internal precession of the device, thus forming a clock. Visually, you can imagine this turning about until it finally comes up. What's very interesting, if you go over the history of atomic clocks, the very first one was built at the National Bureau of Standards, NIST's name before the 1980s, using transitions in ammonia. This is a large object. It was accurate at part 10 to the 11. It wasn't the best clock, obviously, but it was the first of its type, using fundamental physics. But what's hard to understand is how getting an accuracy in time and fixing the speed of light allows you to start developing new technologies. In particular, it allows you to develop where you are on Earth because you know where you aren't. And also you know where, say, other objects are. So if you launch a set of constellations and this constellation has many satellites, each with a clock broadcasting its timing, you can find your place in four-dimensional space-time if you have the clock signals of four of these clocks to reference against where you are presently, and if you know where they're located. This, along with the geographic information systems and pervasive wireless, allows for navigation anywhere on Earth. This is the global positioning system. And so you have quantum technology as a base which enables a much more applied technology with dramatic human benefit. But what's hard when you do this is to project the future. And in particular, here is the current miniaturization that we've been doing at NIST in making these clocks very small. There's obviously commercially available now chip-scale atomic clocks. But what's hard to predict here is that the pervasive navigation and wireless given by quantum technologies enables a transition and transformation of the taxi market, as evidenced by ride-hailing services and ride-sharing services. And so it's the old Danish adage, right? Prediction is hard, especially about the future. What I like to think about, and what I encourage you to think about, is in this space we're focused in on base technologies, things that enable other technology, and we want to get those base technologies right. What are the base technological opportunities, broadly speaking? One of these is in quantum sensing. And I look at quantum sensing with two basic subthrusts. One subthrust is in accuracy via physical law. That is to say that you say quantum mechanics we believe to be a pretty good theory for describing how things behave. If we have a quantum mechanical system we understand well, it is reproducible in many different places on the Earth. And that concept of indistinguishability, for example, used for atomic clocks. You could take other concepts like the physical constant of the speed of light, and then use that to interconvert between distance and time. You can use the quantization of charge implied by QED to use the fact that electrons are quantized to calibrate electrical currents and voltage. This use of accuracy has actually been codified in what's called the Quantum SI, or Quantum System International. This is the system of units that is adopted and finally being used across nations everywhere on Earth now, where we trace all of our meteorological quantities, like mass, time, temperature, to quantum standards. At the same time, quantum measurement also enables new modalities of measurement, where you can measure maybe where you couldn't measure before, something you just couldn't see before. For example, in magnetic resonance imaging, looking inside the body, where you're trying to beat a limit set by sort of standard measurement techniques, sometimes called the standard quantum limit. For example, where quantized light, squeezed light, is being used in the laser gravitational interferometer, or LIGO. And you can also maybe look in areas, for example, where you're trying to go faster or to get better bandwidth, and for example, measuring brain activity, where entangled atomic sensors may be a new path forward. Another key technology is in quantum computation. And this also breaks into two basic areas, quantum simulation, and then the ideal programmable quantum computer. Quantum simulation, I often liken it to the challenge of simulating the Schrodinger equation, which is, like many other equations, hard to solve. We already have examples of analog simulators used for the Navier-Stokes equation, another very challenging equation. And of course, here is a picture from the University of Maryland's team using a wind tunnel to simulate the Navier-Stokes equation in a very controlled environment. In a similar way, a quantum simulator is a system that emulates Schrodinger's equation in a very controlled environment and allows you to develop new classical knowledge of what this is and why it behaves as it does. This allows us to actually change our humanistic and computeristic understanding what quantum mechanics is and how it behaves. So it's a very powerful and useful technique. But the ideal case is the programmable quantum computer, which is now actually really moving from lab to systems engineering. And as I'll talk a little bit more about, from these programmable computers, we actually also have to start looking at the opportunities of networking these computers together, and thus the field of quantum networking. Tremendous opportunities await us, and you've heard much about this over the last week. I won't belabor those points too much here. So how do we realize this outcome? Back in 2017, we saw a tremendous uptick of industrial investment and worldwide investment in quantum information science. You may have heard about the Gartner hype curve. This is a hypothetical graph where the bottom axis is time and the left axis is your estimated final total market for a field. And one of the things that was being speculated on with respect to quantum information about a few years ago was that we were kind of on this initial exponential growth of estimated final market. But there was some concern, right, that we would misestimate that there would be an estimate that it was much smaller and then some eventual growth. And a challenge you look at is how do you actually maintain a research and development program that enables you to get to the real final market in a way that's positive for the nation. And to give you a sense of why this was kind of, and still remains a bit of a hype area, when I was traveling through National Airport back in April of 2019, we have these signs right off the shuttle where they're talking about quantum information science. It's a small field, honestly, but nonetheless very impactful. So what is the government's role here? Well, the way I looked at it is that if you don't do anything, the actual market sort of grows a little bit, and then it can actually shrink because the government's often an early adopter of these technologies, and it's a key driver of the workforce and of the next generation of science you need to make progress. So with no government response, the actual final market ends up being quite small. Or if it's larger, it's not in the United States. But if you do put a government response in, perhaps that actually is a slight negative in the initial market growth because the government runs slow. But long term, you actually get much closer to achieving that final goal of a large and effective marketplace. So how do we achieve those outcomes? Well, now we're going to pivot a little bit towards the question of science policy. What are the policies you need to get to these frontiers? And the quintessential document in this space is Vannevar Bush's report to the President, Science, the Endless Frontier, also responsible for the formation of the National Science Foundation. And I encourage those of you interested in the space to read it because it's the foundational document for modern science policy. But in this, Bush lays out a thesis that there is a virtuous cycle of innovation from science to technology to human capabilities, which leads to new and adaptive behaviors and which leads to growth for the economy. Now, a little bit what's missing here is, of course, it also leads to strife. We've heard a lot in the press over the course of the last several years of how various other emerging technologies could have very negative impact on various stakeholders or are having negative impact from election interference to other things. And the question really becomes, when you have a new technology, how do you integrate the public purpose earlier? Now, I mentioned this because, of course, one of the reasons that I'm now at the Belfer Center is to investigate this question as part of the Technology and Public Purpose Project. So I'll talk a little bit more about that at the very end. But my underlying thesis in the work I'm doing this year is to better understand how we can actually link this process up, so not just do funding here and regulation here, but to have a complete community around each of these subcycles to ensure that impacted stakeholders have a voice throughout the process and to ensure that the technology as it develops reflects our scientific understanding and our technological understanding of where it can go and what impacts it can have. Fundamentally, I'm a person who believes that it is the people that make space technology happen. New technology just doesn't emerge from nothing. It's hard effort by many. And so in many respects, my project now is really trying to build from that thesis and to better understand how we get great people attacking good problems, leading to good outcomes. So I got very interested in this, as you can see. I am a physicist by training, but nonetheless, when I was asked if I might help the White House Office of Science and Technology Policy to build the nation's quantum information science policy effort, I ended up saying yes, and going down to here the Eisenhower Building, adjacent to the West Wing of the White House. And inside this Eisenhower Building, we have the Office of Science and Technology Policy, where I took on the role of Assistant Director for Quantum Information Science. This is from my first day there, late December of 2017. And the real challenge, of course, is when you take on these roles is to ensure that the government is providing decision makers, that I, as a government scientist, I'm providing decision makers with the best possible advice and giving them the best options that are good for the nation. And the real challenge here is to ensure that a public good actually arises as the science progresses. So this is not just about doing great science, it's about ensuring great science leads to great outcomes. So how do we do this? How do we approach this for quantum information science? Well, the first thing we did is we got the team together. And we have the National Science and Technology Council, which is an interagency group across all of the U.S. government agencies working in science and technology. And we focused on integrating the 13 U.S. government agencies that work in quantum information science, making certain that all of our activities worked well together. And that led to the formation of the subcommittee on quantum information science here. This is an image from our first meeting. Many of these faces you may recognize. And this was and is co-chaired by Department of Energy, here with Steve Binkley, NIST, Carl Williams, and National Science Foundation, Ann Kinney. And It coordinates today the National Quantum Initiative and other quantum information science research activities. But we also recognize that there are substantial security implications and national security considerations around quantum information science. So we formed a second subcommittee called the Economic and Security Implications of Quantum Science, or ESSEC subcommittee, led by the Department of Energy, Department of Defense, and National Security Agency, really to ensure that we make the best economic opportunity and best technological opportunity out of this before it becomes a national security threat. We also engage external stakeholders. It wasn't just internal to the government. So we've hosted a summit at the White House, the first summit of its kind. Here is Undersecretary DeBar, along with the NSF Director at the time, France Cordova, Walker Penn, and Mike Griffin from NIST and DoD. And we also had a number of stakeholders from around the community, more than 120 people, including international and all the different stakeholders across the U.S., to dig in deep on many of the challenges in the policy space. This synthesized along with our internal efforts in this National Strategic Overview for Quantum Information Science, which I encourage you to read if you want more depth in what we're doing in quantum information science and what the policies are for the U.S. government in this space. But the key takeaways that we recognized as a community back in September 2018, that we needed to focus on a science-first approach that aims to explore the quantum frontiers. These are problems whose solutions enable transformative scientific and industrial progress. We also needed and continue to need to build a quantum smart and diverse workforce to meet the needs of this very growing field, to encourage industry engagement so that industry, government, academia continue to work in concert in a cooperative manner to meet these needs, and then also to have the key infrastructure in place so that as hard technical challenges arose, no one actor had to pay for it all. At the same time, we had to find the right balance between enabling economic growth and maintaining national security in the space, and to continue to develop and expand our international collaborations and cooperation in the space. This is not us versus them. This is a worldwide scientific effort that we can work in together to build a worldwide marketplace for quantum technologies. So now we have policies. What's the next step? Well, it's to build institutions. Recommendations are well and good. It is their implementation that matters. And the institution that drives the nation's effort in quantum information is actually the National Quantum Initiative, passed at the end of 2018 after 1 year at the White House for me. And this is the signing here. You can see Michael Kratsios from the White House Office of Science and Technology Policy, who was really the key driver on the political side for ensuring that quantum information science is making the progress it can. This calls for 11 years of sustained effort led by the Department of Energy with new centers and new programs, the National Science Foundation also with new centers and new programs, and with the National Institute of Standards and Technology, or NIST, my home agency, with the creation of an industrial consortium along with the expansion of their core programs. The coordination efforts called for in the legislation build upon the coordination I've already described using the National Science and Technology Council, along with the National Quantum Coordination Office and an external advisory committee. These institutions ensure that we're in it for the long haul, that we don't have to suddenly shift gears because of political winds, that we can really focus on getting the right science and technology built. How do we enable the innovation ecosystem? The choices that I looked at drew from my experience, hard-learned lessons at the Joint Quantum Institute and the Joint Center for Quantum Information Science. These are joint centers between NIST and the University of Maryland, which focus on physically co-locating students, postdocs, professors, and staff scientists so that you can learn from each other, to having dedicated infrastructure that ensure good communication and conversations and opportunities, keeping a long-term focus so you're not constantly chasing the money, and making certain you have great talent coming in, going out, and good information coming in, coming out with strong visitor programs, strong seminar programs, strong educational programs. Also, you have to figure out how to detect transfer in this field where the time horizon is very long, and how to have good interfaces with the OEM community and skills training and transfer. Now, if you look at how this is being implemented, we have the Department of Energy Quantum Information Science Centers, which you've heard quite a bit about, and just tremendous investment. And then also the National Science Foundation and Quantum Leap Challenge Institutes. Overall, we're looking at nearly $1 billion over 5 years dedicated to these types of centers. At the same time, we want that industrial engagement. So the NIST approach is the Quantum Economic Development Consortium. And you can read about it at quantumconsortium.org. But essentially, this brings together the key stakeholders working in quantum industry, including the supply chain, large startups, small startups, large tech companies, and some of the nonprofits that work in the space, with the government, to ensure that the technology we need is available, that the workforce continues to be available, and that we cooperate where we can, while still maintaining a good market-based approach for actual emergent technology. We also formed the National Quantum Coordination Office, and you can read about it at quantum.gov, which is now the official site of the Quantum Coordination Office. And here's our seal, the eagle and a cat. The office I led, it is now 18 months old. I passed the torch of this office to Dr. Charlie Taha, who is available on Twitter if you want to find him there. And Charlie took over in July, and it's been doing gangbusters since, obviously. But this provides a fundamental institution that allows all the agencies to continue their conversation together. Okay, so now we have these institutions. How do we now integrate and expand, particularly how to expand the community? So one of the things we did is we built the Quantum Frontiers report, which just released. You can see it on quantum.gov. I'll talk about that more at the end. But this is really based on a consultation with the community to identify the priority areas for investigation through requests for information, and we're looking at workshop reports done by many, many agencies across the last several years, along with nonprofits. And I mentioned those Quantum Frontiers as key to our policy program. Well, this is really trying to articulate what those 5 to 10 year horizon research opportunities are that enable new technological applications. Now, I'll talk about that more, but I do encourage you to read the report if you want to get a much more nuanced take. And the principle here is very simple. It's not the government's job in this space to determine what the development pathway is. It is the community's job, because it is a science space. If we knew all the answers, it would be a technology space, but it is not. We do not know all the answers. We don't even know all the questions to ask yet. So we're very excited about those opportunities. Now, as an example of how Quantum Frontiers evolve, when I got started working in the policy space, quantum communication was the general rubric that we applied to looking at how information in quantum systems is transferred at distance. And the challenge was that quantum communication was often becoming synonymous with a very particular niche technology, which is quantum key distribution. But there's tons of enabling technology around that: the sources, the detectors, the fibers, the transducers, low-loss elements. And there's a tremendous set of opportunities even for small-scale quantum repeaters in this space. But at the same time, the long-term horizon is out here, connecting sensors together with entanglement for a quantum Internet of Things, and enabling quantum cloud computing, a quantum computer on the cloud that you can be entangled with. And that entanglement then allows you to run interactive protocols, which are beyond what you can do with classical compute, or what you could even do with a classical interface to a quantum computer at distance. And there's a recent bill that's been proposed to actually fully fund a quantum internet network. Tremendous effort at the Department of Energy to put together a blueprint for this. And if you want to read the sort of overall strategic vision for why we're investing in quantum networks, I do encourage you to take a look at this strategy document we put out at the National Quantum Coordination Office back in February. But the key thing here is a refactoring, a change of language from quantum communication to the longer term horizon, which is quantum networking. And I'm very excited that that change is enabling now new research programs and new investment and new growth. On the workforce front, I looked quite a lot at what's happening in other scientific areas, and I imagine you have done the same. Here's a great graphic put out by Compass, which is looking at it in biological spaces, how students transition from graduate study to eventually some final job, either as a government researcher, industry researcher, a tenure track, whatever it may be. And one of the things that I learned over the course of my time working downtown was that starting here in your workforce development is far too late. If you want to get a broad and diverse workforce, you actually need to start much, much earlier. And so one of our things here was to try and bridge computer scientists, physicists, engineers, mathematicians by getting them at an earlier stage. And that was why we launched the National Q-12 Education Partnership, which is focused on getting initial quantum-related concepts taught at the 7th, 8th grade through 12th grade level, and then integrating that with curriculum at the undergraduate and also community college and technical colleges to then ensure that there's a panoply of different possible pathways to getting into quantum technologies. And we really are thrilled that so many industry players have come to it, along with the professional societies, to ensure that we have great materials, that we have good training for teachers, and that can then get into the classroom in an effective manner. I encourage you to take a look at that if you're interested on the education side. And then on the international cooperation space, one of our first actions there was the signing in December 2019 in Tokyo of the Tokyo Statement on Quantum Cooperation, which you read about on state.gov, which is an affirmation of the US-Japan relationship in quantum information science and technology. And it's the first of its kind, recognizing our opportunity to work together, particularly around the people, around coordinating our research and cooperating in the industrial space. Okay, I provided some backdrop. Now it's time to talk about those frontiers. So this is not the Quantum Frontiers Report frontiers. These are Jake Taylor frontiers. But there are a lot of parallels. And so for me, I'm really interested in the challenges ahead in qubit physics. What new materials and new applications do actual individual qubits have? In networking physics, both classical networking theory, the new protocols, new detector systems, and how we actually connect these things up effectively. This science of quantum engineering, which is both new applied math technologies, new electrical engineering and computer science technologies, new ways of understanding how to characterize and integrate different disparate quantum systems to achieve actual system integration, and having the right engineering models that allow you to do that on paper before you build the darn thing. There's a whole new set of opportunities and algorithms to run on current and near-term hardware, so-called NISC-era algorithms, noisy intermediate scale quantum. And here I really am hopeful that we're going to get a much deeper understanding of quantum mechanics, particularly in chemistry, but also its application optimization and a wide variety of new and unknown areas. In error correction, there's a tremendous set of opportunities for actually doing better on error correction. It's been a very fruitful year for that if you've been tracking the literature. But it's not just about full-scale quantum computers. It's about understanding quantum materials. It's about understanding quantum gravity. It's about understanding the algorithms behind error correction and what you can do from that. And then finally, and this I'm very excited about, is developing an expressive language for quantum mechanics that enables to write algorithms and to develop new applications. We don't have the high-level languages that we really need to understand quantum algorithms, to understand what a quantum simulator does. And developments in that space are very promising. So I'm going to now conclude in the last little bit of time with some of the work that my group has been up to, roughly while I was away doing this policy work. And we're focused, this is now a little bit, I'll keep it kind of quick, but we're focused really on two basic areas. One is what I call quantum devices for technology. These are the devices that are robust, that can be engineered, they can be made compact, they can be made interoperable, and they actually have some pathway to go from the bench to product. And one of the areas we're looking at there is actually the role machine learning plays in enabling the actual application of these somewhat analog technologies to the real world. And then the other area is really quantum sensors for physics, which is how do we explore complex systems in new ways, and how do we examine the assumptions that we already had about systems and look for new physics using quantum sensors. On the technology side, there's a bunch of set of opportunities to talk about. Actually, this vortex circulator paper just showed up on the archive, but this is, for example, an approach to making a microwave circulator with high bandwidth that operates at very low magnetic field and is very compact, made of just a few adjustment junctions. There's also some interesting efforts in utilizing sound and circuits together, a so-called surface acoustic wave transmon, or SOLMON. And you have a paper on that, which you can read about. There's many others working in that space as well. The idea here is to try and get away from using these centimeter scale microwave cavities to instead millimeter or micrometer scale mechanical cavities. In the cell phone industry, of course, we use mechanical filters rather than electrical filters because they're very high quality and very compact. And we have hopes that this can be applied in the supercomputing qubit space. There's also a very interesting applied project we've been doing, led by Justina Zwolak at NIST, my old postdoc, and we work on this together now, which is a software suite for tuning up quantum-related experiments, particularly semiconductor quantum dot experiments, which have many, many knobs and have to be tuned to a particular operating point before you can do qubit experiments. And that auto-tuning software has had a series of successes, including a sort of cold start auto-tuning now, where you have a fridge, you cool it down, you put a device in, and it tunes. And then finally, we've been working also on this expressive language problem space for quantum compilers, which is how do we actually efficiently do multi-qubit quantum compiling? What is the optimal approach there? And what can we learn about the language of expressiveness for quantum circuits? I'm going to talk a little bit more about that in a moment. I do want to also mention on this sort of sensors for physics side, there's two things that I'm very excited about. One is some work I've been doing in collaboration with the team at RIKEN in Japan, the Yasunobu Nakamura's group, where we're looking, for example, at a many-body physics, in this case a BKT transition. This is a topological phase transition that can occur in arrays of Josephson junctions. Essentially, you have a transition to lots of vortices in that array. But we wanted to probe that using a non-standard technique, in particular using the techniques of circuit QED. And that allowed us to probe these systems at much lower temperature than anyone had ever done before and see many new interesting phases. This is a plot of the cavity transmission spectra. It's a function of the frequency of a probe versus the applied flux through an array of these devices. And you can see that there's this symmetry as you go from 0 to pi flux, going through the device, and a variety of very interesting features which we're able to associate with different vortex phases of this lattice system. And then the other area, which I'll talk quite a bit more about now, is actually trying to search for dark matter and traces of quantum gravity using quantum sensors. On the language side, let's just talk about that briefly. So, you have a human interface, but our human interface to quantum machines is very rudimentary. Various industry competitors notwithstanding, we don't really have the tools for an expressive quantum program in human expressible units. So, if you think about how Facebook is built, it's built off of C++ and Fortran and other high-level languages, which are built off of low-level languages, the so-called assembly languages, which are in turn built off of machine code, right, which in turn is run on the hardware. And in the quantum space, we've had, by the way, a compiler, of course, is the thing that goes all the way from up here, the high-level code, down to here, running on the actual hardware. And we've had a lot of progress on different elements of this stack in quantum information over the last several years, which is very exciting. But fundamentally, we're faced with a really interesting challenge. And that is that we have two basic languages that describe quantum mechanics, in particular the operation of a quantum computer. One is the language of circuits, in which you have qubits going along temporally, vertically laid out here in space, with different operations between them. And the other language we have comes from physics, which is the idea that you have some sort of Hamiltonian with some Lie algebra that describes the terms in the Hamiltonian, and exponentiation of the Hamiltonian leads to evolution. In both cases, you have to specify what you start in and what you measure, and yet we don't have a good way to interoperate between these two different descriptions, between this sort of Lie algebraic picture and the circuit-based picture. And that's a real failing, because it prevents us from taking our best physics intuition and applying it to circuits, or best circuit intuition and applying it to physics. And neither of these, of course, is a high-level language. The concept of a for loop doesn't really make as much sense here. So those high-level primitives aren't exist. Now, I guess one of the key things that really guides this compiler work is recognition that we actually want to do it in the quantum error correcting regime. And so that also means that you kind of have to use gates that probably aren't fully transversal. You probably want to use magic state distillation to produce a non-Clifford gate. And usually you do that by some sort of noisy magic states, purification circuits, followed by post-selection of the less noisy magic states, iterating this around in order to get a high fidelity magic state. The main thing you should take away is that the non-Clifford operation of a circuit in quantum error correction is very expensive compared to the Clifford operation. So consequently, most compilers are now designed around minimizing the cost of the non-Clifford gate. And what's been interesting in this case was that actually the optimum approach for the two-qubit case was actually, until recently, not known. We had suboptimal approaches, but there was no synthesis algorithm where you could hand your compiler a unitary and then receive the circuit to apply and know that it was the optimal circuit. And one of the challenges here has to do with some mathematics around the Clifford plus so-called T gate, which is a pi over 8 gate around the z-axis. So one of the things that my student Andrew Gladow did, and our old Hartree fellow at Quicks, Neil Julian Ross, along with myself, was to use a simpler gate set. So rather than using the Clifford plus T, we essentially use the Clifford set here, and then this S gate, which is like a pi over a forward rotation about the z-axis, we made a controlled S gate for our actual desired two-qubit gate, rather than this controlled X gate here. The controlled S is a non-Clifford gate, but it's symmetric. And that actually makes it much easier to then solve this two-qubit compiling problem. And that allows us to basically take some circuit, put it in normal form, find the relations of how to reduce it down, and essentially apply these relations in order to get a normal phone. And we also have proof of optimality. We have a software package, which is going up on GitHub, I hope very soon, which allows you to basically hand a unitary over and get an optimal circuit back. Now, this is really baby steps still in the compiling space, because we're now doing optimal two-qubit. And of course, we actually need optimal n-qubit, and we need a better language that describes it. But one of the things that we're learning in this is how the math behind these types of circuits really matters. So it's very interesting to make some progress there. The other thing that I'll probably close out with this is trying to understand what we can do with quantum sensors in the area of measuring things that are massive. And the background here, of course, is that we've always grown up with this idea that cat states, that is a superposition of a massive thing in two different states, is probably not very long-lived. And we'd love to take that intuition and take that concept and really come up with ways of testing it, particularly around the actual concept of mass. One of the things that Roger Penrose, a current Nobel laureate from this year, is very famous for is describing how mass superpositions probably aren't compatible with gravity. Well, we don't know whether that's true or not. We have to test it. And so, and there had been some tests which are putting some restrictions on the so-called Penrose-Degaussy theories. But the main thing you should understand is that it is possible in the laboratory today to create massive superpositions. Here's a great paper from Ralph Sholkoff's group. Yuan Chu was leading that effort before she went on to her faculty position. And what they did in this experiment was they had a transmon qubit. Here's the transmon, aluminum superconducting circuit on top of lithium aluminum oxide block. And they had a small piezoelectric disc here, this aluminum nitride transducer, which produces a quasimode in the bulk here, which is a resonance, a phononic resonance. So this is motion, sound. And what they could do is they actually had strong enough coupling that they could take the non-classical state of the transmon, a superposition of 0 and 1, and map it into the sound, a superposition of no phonon and one phonon, no phonon and one phonon, and then swap it back. And they could see the reduction of Ramsey coherence as they held it for longer and longer. And what that tells you is that they're able to maintain a non-classical superposition of a mass in two places, roughly, for in here, some 30 or so microseconds. So what are the consequences? What can we test with experiments of this nature? It turns out you can maybe one day test something very interesting. To understand, how much progress we've made in terms of getting things down to a quantum regime, it's important to realize that when you have a mass and it's moving, so here's, for example, a mirror on a pendulum, similar to some of the works by other teams. Here is a sphere levitating in an optical trap from Vannevar Bush's group and also the team at Vienna. And here is a small piece of silicon nitride membrane surrounded by lots of other silicon nitride membrane, making a very interesting phononic shield so that this central area here can actually nearly freely move and be very well isolated from its environment. And what you can find is that the quantum mechanical Q, that is the inverse time of adding or subtracting a single phonon, including a thermal phonon, so it's much faster than just the damping rate. Here was about 4 megahertz at room temperature. Here it was about 20 kilohertz held in high vacuum. Here it is about 200 hertz held in low vacuum. And at medium temperatures, if you could take this and cool it down, you get this down to about 400 hertz. If you cool this down to dilution refrigerator temperatures, you're looking now at coherence times in the order of 5 seconds, which is starting to get very interesting. So why is that interesting? Well, I want you to consider the coupling via gravity between two different objects. You can ask, if objects are coupled by gravity, does it entangle them? And believe it or not, we don't know the answer to this question yet. If you believe effective field theory, you believe the low energy theory of gravity is probably quantum, then you should say yes. But if you believe in some emergent gravity theory, you might say no. And if you think about a harmonic oscillator, here's a spring and here's the mass, here's a spring, here's a mass between Alice and Bob with a gravitational interaction between them, you can take the Newtonian interaction, which is a perfectly fine low energy description of relativity, and expand it out. And what you find is that the interaction between Alice and Bob is given by this prefect here, Newton's constant big G, the mass is divided by the distance cubed, and then the length scale of these two harmonic oscillators and their displacement from their equilibrium. Unfortunately, big G is very small. So this leads me to what I call the sort of golden rule of terrestrial quantum gravity, or the dismal rule of terrestrial quantum gravity, which is that there is a natural combination. So if you look at that big G, you have a mass twice and a radius cubed, and then two different positions. But if you take the harmonic oscillator length, a natural physics unit, square root of h bar over 2m omega, and you write it out, you see that these masses cancel, and I have this mass over radius cubed, mass over distance cubed, that's a density. And so there is actually a bound on this density for terrestrial units, because we can't make things that are that dense here on Earth, which sets this frequency scale, zeta, as the square root of big G times density, and it's about a millihertz. What that should tell you is that if you want to do an experiment with quantum gravity, you're going to be fighting against this millihertz scale. Everything's going to be very, very slow. And that's going to govern any entanglement experiment that you can conceive here on Earth. And so we want to think about entering the ultra-coherent regime of massive objects. Very interesting domain that we may get to as we pursue ultra-coherence for quantum systems, particularly quantum sensors. And I'm going to define it simply that an ultra-coherent massive object has a coherence time for a superposition of two phononic Fock states that is in excess of this terrestrial quantum gravity constant. Or alternatively, its quantum damping rate is less than zeta. So you have to have quantum coherence times of 1,000 seconds for massive superposition. But while this does not get realized, we're actually now, as I mentioned, in principle, only a few orders of magnitude away in quantum coherence times. For example, using the work from the Copenhagen team. And we know that the QF products for cryogenic materials don't limit you, so there's no particular theoretical reason you can't get to that low values. We also know that for free-falling particles, actually background gas limits could be even better than this. So it's a very interesting question, which is how close can we get to this ultra-coherent regime? And if we enter it, what can we learn? One of the questions is, what are the fundamental limits opposed by quantum mechanics for the detection of small forces and impulses on these types of devices? Another is, what can we learn about quantum effects in gravity? So we have a tutorial on that if you want to read about it in the archive, along with Phil Stamp. And then one of the things we've been looking at is what else can we detect using sensors in this regime? And in particular, we've been very interested in the detection of dark matter through its gravitational interaction. And then also, what other physics targets can we look for? So I'm not going to go deep on dark matter. It's obviously not really a quantum information science thing to most people here. But I think you have probably heard that we believe a lot of the universe is made of dark matter. And the evidence is pretty broad as to why. I'm not going to go into that. But what I will say is that what we don't know much about dark matter is anything other than it gravitates. It could be small black holes or objects that are terrestrial in size. It could be ultralight particles that have very weak coupling to the standard model. What we've been interested in here has been looking at the energy scale we expect new physics to emerge, the so-called Planck scale, which is set in natural units. It corresponds to a mass of about 20 micrograms or so. And looking for dark matter in that regime, where you may just have residual particles at that scale. And what's very interesting is dark matter in that regime actually gravitates strongly enough that it can interact with the ultra-coherent sensor and leave a noticeable signal behind. So let's talk about that briefly. I want you to imagine that I have a dark matter particle up here, and I have a very coherent mass that I can probe using the state-of-the-art in quantum sensors and beyond. Now, if this dark matter particle is moving quite rapidly, we think that there's a dark matter wind, probably about 200 kilometers per second. When it's moving by, it has a scattering off of this mass due to gravity, right? So it bends a little bit, and as it goes by, the mass gets an impulse going this way. This is just gravitational scattering. If you look at the size of the impulse, it's given by this gravitational constant, the mass of the big thing, the mass of the dark matter, divided by the impact parameter, the distance between this straight line and the center of the mass, and the velocity of this object. So this is a change in momentum, which you'd like to measure. So the question now becomes, can you observe these individual events? The dark matter wind doesn't produce many of these particles going by if they're Planck mass. You know, some tens per year per square meter or so. But they happen very fast, sub-microsecond or so scales. But they do impart a large momentum. And the change in momentum is actually something you might be able to measure because, if you're not familiar, for free particles or for particles well above the resonance frequency, masses well above a mechanical resonance, measuring momentum is actually a so-called back-action-free measurement. It can be measured to very high accuracy with small back action if you're clever about it. And so that actually led us to propose the following sort of bubble chamber concept, an array of these types of sensors. And what you can imagine is a dark matter particle goes flying through the array, and it leaves behind a correlated track of motion as it goes through. And this correlated track of motion can then be measured and pulled out of many other possible backgrounds, largely because of the very weak interaction of those particles and the fact that the gravitational action is a long-range interaction. And so it impacts a wide number of the particles as it goes through. And there's a nice little sort of public science blurb put up in Nature Materials and a more recent one on the NIST website if you want to read about this type of path. So now let's return to the point of this talk, which is to talk briefly about the frontiers. And so what I'm very excited about are these different areas for further exploration. And as I mentioned, we recently, and the Quantum Coordination Office, I should say, recently released the Quantum Frontiers Report, which digs in deep on these opportunities. I really encourage you to go to quantum.gov and take a read. I think there's a great set of opportunities awaiting us. With that, I want to close and thank you very much for your time. And also I want to thank in particular Andrew Glado and Julian Ross, who were essential in our quantum compiler work. Obviously, it was Andrew's thesis topic, and Julian, who's our quantum compiler guru, really made it all happen. And then on the dark matter front, Dan Carney, who is my postdoc, now moving to Lawrence Berkeley Laboratory, Suruchi Ghosh, and John Kunyaman, who have been the graduate students working on that project. Thank you so much for your time, and I look forward to your questions.